Welcome. Today we're really diving into the physics of the machines we rely on every day for radiation therapy. It's more than just knowing the controls, isn't it?
Oh, absolutely. It's about understanding how they work, why they're built the way they are, and what that means for treating patients. This is, core knowledge, especially for anyone preparing for exams.
Exactly. So we'll start a bit with the history, the Cobalt 60 units,
Yeah.
but then really spend our time on the modern workhorse, the Linear Accelerator, the LINAC.
Right. We want to trace that whole path, how the radiation gets generated, how we shape it, understanding the components, the beam properties, the sort of practical side of things. It's fundamental.
You need that foundation to grasp treatment planning, why certain things happen, maybe even troubleshoot when things look a bit off.
Precisely. Getting that mental map of the beam's journey, from start to finish is just key.
Okay, let's get started then. To really appreciate the LINAC, we should probably look back first. The radionuclide machines, the Cobalt 60 era.
Yeah, before LINACs became ubiquitous, Cobalt 60 was really the standard for external beam. The source itself, Cobalt 60, is radioactive. It's made by taking stable cobalt-59 and hitting it with neutrons in a reactor.
And what made it work for therapy? What were its key properties?
Well, the main thing was its decay. It undergoes beta-minus decay, turning into nickel-60, but in an excited state.
Okay.
And that excited nickel-60, it immediately wants to get down to its ground state. It does that by emitting gamma rays, specifically two main ones, 1.1, 7 mega electron volts, and 1.33 mega electron volts.
So high energy photons.
Yeah, and we often just average them. Think of it as about 1.25 mega electron volts.
Yeah.
Perfect for getting dosed deep inside the body.
What about how long it lasted? I mean, it's decaying, right?
Right. It has a half-life of 5.26 years.
Yeah.
So every 5.25 years, roughly, the source activity is cut in half.
Which means you had to replace it periodically.
Exactly. But that half-life was sort of a good balance, long enough to be practical for years, but you always had to account for decay in your dose calculations. It also had a high gamma constant and high specific activity, meaning you got a lot of radiation from a physically pretty small source.
That small source size sounds good, but it led directly to one of Cobalt's main drawbacks, didn't it? Penumbra.
Spot on. Penumbra, that blurry edge of the beam where the dose falls off. With Cobalt, the big player was geometric penumbra, P sub G. And that's purely because the source wasn't a perfect point. It had a real physical size as...
Yeah, the formula, that's one of those must-knows. Can you walk us through it again?
Sure. It's basically similar triangles. Geometric penumbra, P sub G, equals the source size S times, let's see, the quantity, SSD plus depth D minus SDD, all divided by SDD.
Okay, so SSD is source to surface distance, SDD is source to diaphragm distance.
Right. S times SSD plus D minus SDD over SDD.
So looking at that, what makes the penumbra, that fuzzy edge, worse?
Well, a bigger source size S, obviously,
Right.
retreating deeper, so a larger D, and maybe counterintuitively, a smaller SDD.
Smaller SDD. So the collimator jaws are further from the patient.
Exactly. Think of the shadow diverging more. The further the diaphragm is from the source, the wider the shadow's fuzzy edge gets by the time it hits the patient depth.
Okay, I see. The angle spreads out more. So to make it sharper on Cobalt, you wanted a small source, a large SDD, get those collimators or trimmer bars closer to the patient, or treat shallower if possible.
Precisely. That was the geometric part. Then you also had some transmission penumbra, radiation getting through the jaw edges, and scatter within the patient, fuzzing things out too.
And there was that mechanical shutter issue too, right? Timer errors?
Yeah, shutter error or timer error, especially for really short beam-on times, that could be a factor. All these things sort of pushed towards developing something better.
Which brings us to the star of the show, the Linear Accelerator, the LINAC.
The modern workhorse. Totally different principle, no radioactivity. It uses high-power microwaves.
Like in a microwave oven, but way more powerful.
Exactly, much higher power. Uses those microwaves to accelerate electrons up to really high energies, typically, 4 to 25 mega electron volts.
And the beam isn't continuous like Cobalt, it's pulsed.
Right, thousands of little pulses per second. And understanding the sequence, the order of components inside that LINAC head is just critical. It tells you how the beam is made, shaped, and where things might go wrong.
Let's trace that journey then. Where does the electrons trip start?
Well, you need power first, right? So the power source provides the basic electricity.
Okay, then that raw power needs shaping.
Yep, goes to the modulator. That thing creates the really high voltage, high current pulses needed to fire the electron gun and the microwave source. It has a key part called the pulse forming network, or PFN.
PFN. Got it.
Yep.
Okay, pulses go to
The electron gun. This generates the initial cloud of electrons. It's usually thermionic emission, heat up a filament, electrons boil off, kind of like an old light bulb filament.
Now, here was that interesting point you mentioned earlier. For a higher energy X-ray beam, like 18 MV, you actually need less current from the electron gun than for, say, 6 MV.
Yeah, it seems backwards, but think about how X-rays are made in the target Bremsstrahlung. That process gets much more efficient as the electron energy goes up.
Ah, so fewer high-energy electrons can make the same amount of X-ray dose as more lower-energy ones.
Exactly. You need fewer bullets if each bullet carries more punch to get the same overall effect.
Clever. Okay, electrons are generated. Now the microwaves to push them.
That's the microwave source. Two main flavors here. For lower energies, maybe 6 MV or less, you often find a magnetron. Think of it as generating the microwaves itself.
Okay.
For higher energy machines, you usually have a klystron. A klystron doesn't generate microwaves. It amplifies a low-power microwave signal up to the very high power needed.
Magnetron generates, klystron amplifies. Got it.
Oh.
And these microwaves need to get to the accelerator without problems. That's the waveguide.
Yep. The waveguide is like a special pipe for microwaves. Inside, you often find a circulator, kind of a one-way valve for microwaves. Stops reflections from going back and wrecking the source.
Oh.
And the waveguide is usually filled with an insulating gas like sulfur hexafluoride, SF6, to prevent sparks, arsing with all that power.
SF6 gas. Okay. So electrons and microwaves meet up in the
Accelerator structure, or accelerator guide. This is the main event. It's a long, precisely made tube under high vacuum.
vacuum is key.
Absolutely. Electrons travel down, surfing on the microwave fields, getting accelerated up near the speed of light. There are different designs: traveling wave, standing wave. Standing wave is generally more efficient, lets you build a shorter structure for the same energy.
And it makes sense, a longer structure for higher energy.
Generally, yeah. Or more microwave power. Adjusting the final energy involves tweaking the microwave power, maybe the gun current, how the electrons sync up with the waves. It's a fine balance.
Electrons are now super high energy, flying straight. You need to turn them towards the patient. Bending magnet time.
Right. Uses magnetic fields to bend the beam. You see 90-degree bends, but more commonly 270-degree bends.
And the 270 is better, you said. Why?
It does more than just bend. It acts like an energy filter, an energy spectrometer. As the electrons go through those 3 bends, you can use slits inside the magnet path to sort of slice off electrons that aren't at the exact right energy.
Oh, interesting.
So you get a cleaner, more mono-energetic beam hitting whatever's next. Plus, it helps focus the electron spot size really tightly on the target.
Like having a smaller source size in cobalt. Less geometric penumbra.
Exactly. Better energy selection, sharper beam spot. Big advantages for the 270 design.
Okay, beam is bent. Now the path diverges depending on photons or electrons, right?
Correct. Photon mode first. The electron beam hits the X-ray target, usually a thin piece of high Z metal like tungsten. Electrons slam into it, undergo Bremsstrahlung, create high-energy X-rays. It's a transmission target. The X-rays go through it towards the patient.
And if it's electron therapy time?
Target moves out of the beam path, completely retracted.
Okay, back to photons. After the target, the raw X-ray beam is very intense in the middle, right? Peaked forward.
Very peaked. So first it hits the primary collimator. That's fixed, sets the maximum field size, gives the beam its initial cone shape.
And then comes that crucial piece for photons, the flattening filter.
Yes. Cone-shaped metal, thickest right in the center. Its whole job is to knock down that central intensity, to make the beam dose profile flat or uniform across the field, but specifically at a certain depth.
Usually 10 centimeters depth in water.
That's the standard design point, yeah, 10 centimeters.
But messing with the beam like that has consequences.
Oh, big time. First, beam hardening. The filter absorbs more low-energy photons, especially in the center where it's thickest. So the average energy of the beam increases, it gets harder, and it's hardest along the central axis.
And that leads to horns.
The classic horns. Those areas of higher dose near the field edges compared to the center. You see them most clearly at shallow depths, like Dmax, the depth of maximum dose.
Why shallow?
Well, 2 things. At shallow depths, you haven't built up much dose from scattered photons coming in from the sides yet. And the beam is hardest in the center, meaning relatively less dose deposited shallowly there compared to the slightly softer beam edges. So the edges look hot relative to the center, especially near Dmax.
And horns are worse for bigger fields, lower energies.
Yeah, more prominent for shallow depths, larger fields, and lower megavoltage energies. Makes sense when you think about the differential filtering and scatter buildup.
Totally. Okay, so that's photons. Now flip to electron mode, targets out, filters out. What's in?
Scattering foils.
What do they do?
Well, the electron beam coming out of the bending magnet is just a thin pencil beam, not useful clinically. The scattering foils, thin sheets of high-Z material, spread that pencil beam out into a wide, usable field. Often there are two foils. A primary one does the main scattering. A secondary one helps make the final profile nice and flat.
Some machines use scanning magnets instead.
Right. Scanning systems sweep the pencil beam magnetically across the field. Big advantage is less photon contamination compared to using foils. And of course, in photon mode, the foils, or scanning system, are removed.
Okay, beam generated, shaped by filter or foils. What's absolutely next?
The monitor chamber. Super important. It sits right after the filter foils, but before the secondary jaws.
Why is it so critical?
It's the machine's main dose measurement device, usually a parallel plate ionization chamber. It measures the dose rate, counts up the total dose in monitor units MU, and usually has segments to check if the beam is flat and symmetric during the treatment.
So it controls the dose delivery and checks the beam quality in real time. Does it need corrections, like for air density?
If it's an unsealed chamber, yes, absolutely. Needs temperature and pressure corrections, just like a farmer chamber you'd use for calibration.
Okay, monitor chamber. Then downstream, there's usually a mirror for the light field.
Yep, shows you where the radiation field is supposed to be.
Followed by the secondary collimator, the movable X and Y jaws defining the rectangle.
Right. And after that, often we have tertiary collimation, usually the multi-leaf collimator, the MLC.
Ah, the MLC. Amazing tech. All those little tungsten leaves moving independently.
Yeah, 50 to maybe 120 pairs. Each leaf maybe half a centimeter to a centimeter wide at isocenter. They have rounded ends.
Why rounded?
To keep the penumbra consistent as the leaf moves in or out. If they were flat, the penumbra width would change depending on leaf position. Rounded tips give a more constant geometric edge.
Makes sense. And MLCs allow complex shapes, IMRT, but they leak, right?
Yes, leakage is a key thing to know. There's mid-leaf leakage, radiation getting through a leaf, usually low, maybe 1.5 to 3%.
Okay.
Then interleaf leakage, radiation sneaking between adjacent leaves, can be a bit higher, 2 to 5%. That's where the tongue and groove design helps.
The little interlocking edge.
Exactly. The tongue on one leaf fits in the groove of the next, blocking the direct path through the gap.
And the last type, between opposing leaves.
Intraleaf leakage. That's between the tips of leaves coming from opposite banks when they're meant to be closed. If they don't meet perfectly, that gap can leak quite a bit, maybe 10, even up to 50% in bad cases. Really highlights why MLC QA is critical.
Speaking of QA, how accurately do those leaves need to be positioned?
Pretty tight tolerances. Annually, you check position usually to within 1 millimeter. Monthly, maybe 2 millimeters for static positions, but still 1 millimeter for dynamic movements, like in AMAN RT.
Okay. What about electron setups? No MLCs there.
Right. For electrons, we use electron cones or applicators that attach to the head. Then a custom cutout, usually made of Cerabend.
That low melting point metal.
Yeah, shaped to the target. And crucially, you place that cutout as close to the patient as possible.
Why close?
Air scatter. Electrons scatter way more in air than photons. If there's a big gap between the cutout and the patient, the beam edge gets really fuzzy from electrons scattering in that air gap. Keep it usually 5 centimeters or less. And remember, electron flatness is defined and checked at Dmax.
Wow, that's quite the sequence, keeping it all straight. Right. You mentioned a mnemonic earlier.
Yeah, helps keep the main path in mind. How about electrons generate microwaves and accelerators, bending to target foils, measured by monitors, shaped by jaws and MLCs?
Okay, let's try that. Electrons, electron gun, generate microwaves, microwave source, magnetron, claystron. In accelerators, accelerator structure, bending magnet. To target foils, X-ray target or scattering foils, measured by monitors, monitor chamber, shaped by jaws, secondary jaws, and MLCs, tertiary collimation.
Got it. Electrons generate microwaves and accelerators, bending to target foils? measured by monitors, shaped by JAWs and MLCs. It hits the main components in order.
That's actually really helpful. Okay, so we've got the beam made and shaped. How do we check where it's going and confirm the dose?
Well, we mentioned the monitor chamber for the dose, MU, and profile check. Then there are the computer systems.
The R&V systems. Record and verify.
Exactly, critical safety layer. The R&V system knows the approved plan. MU, angles, positions, MLC settings. Before the beam turns on, it checks that the machine settings match the plan. If not, no beam. Big safety interlock.
And then imaging, actually seeing the patient setup. Used to be port films.
Yeah, using the MV treatment beam. Grainy images. Okay, for bones, not much else. Now we have electronic portal imaging devices, EPID.
EPDs. How do they work?
Usually a metal plate converts the MV photons coming through the patient into electrons. Then a phosphor screen turns electrons into light. And an electronic sensor array, often amorphous silicon, captures the light and makes a digital image.
So we get real-time MV images, good for setup checks, QA,
Yeah.
but still limited image quality, right?
Right, because of the MV physics.
Right. Compton scatter dominates at MV, so contrast is poor. That's why for image-guided radiotherapy, IGRT, we often lean on onboard kilovoltage KV imaging.
Because KV X-rays give better soft tissue contrast.
Much better. More photoelectric effect. You can see soft tissues much more clearly. Okay. And the doses from these different imaging methods, that's important, right?
It's impressive for bores.
Hugely important. Need to know the ballpark figure. So regular KV planar ports, just 2D X-rays, very low dose, less than 1 milligray, so less than 0.1 centigrade. Minimal.
Okay.
Kilovoltage cone beam, CT, KVC, BCT, the 3D KV scan, that's more typically 1 to 5 centigrade per scan. Think of it like a regular diagnostic CT or a PET CT dose.
1 to 5 centigrade for KVC, BCT, and the MV version.
A megavoltage cone beam CT, MVC, BCT, using the treatment beam, significantly higher dose, often around 20 centigrade per scan. And the image quality is generally worse than KVC, BCT because of like Compton scatter blurring things out.
20 centigrade, wow. Okay, so KV port 0.1 CAGI, KVC, BCT 1 to 5 CGI, MV, CVCT 20 CGI. Got it. High yield numbers. Briefly, other machines besides standard LINACs.
Sure. Tomotherapy, that's basically a 6 MV LINAC on a CT scanner gantry. Treats helically, slice by slice, with intensity modulation.
And cyclotrons. They accelerate heavier charged particles, usually protons for proton therapy. Also used to make isotopes, like for PET scans.
And proton therapy needs that special energy shaping, right? The SOBP.
Yeah, protons dump most of their dose at the end of their range, the Bragg peak. To cover a whole tumor, you need to layer multiple Bragg peaks of different energies. That creates the spread out Bragg peak, or SOBP, often done with rotating wheels or wedges.
Okay, so we've covered a ton of hardware and physics. Why does drilling down into this level of detail really matter clinically?
It's foundational. Understanding it helps you grasp beam properties, why LINAC penumbra is sharper than cobalt, how energy affects depth dose, things like that.
And huge for troubleshooting and QA, right?
Yeah.
If something's weird with the beam.
Exactly. If flatness is off, you immediately think, is it the flattening filter, the monitor chamber? Is the bending magnet aiming wrong? Maybe the gun? Knowing the sequence gives you a logical path to diagnose problems. Understanding horns explains why profiles look the way they do, especially shallow.
And knowing MLC limits, like leakage, directly impacts how well you can plan and deliver something complex, like IMRT.
For sure. And it helps you understand new tech, like flattening filter-free beams, FFF, or scanning electrons, or MR LINACs. It all builds on these core principles.
And ultimately safety. Interlocks, R&V, monitor chambers, knowing those IGRT doses. It's all about treating safely and accurately.
Couldn't agree more.
Let's try that troubleshooting idea. Say you're treating with 18 MV photons, and the machine flags a big flatness error beams way high on the left side. Walk me through your thought process using the components.
Okay, high on the left, starting at the detector, is the monitor chamber itself faulty on that side? Possible. Go upstream. Flattening filter. Is it tilted? Damaged. Shifted. Also possible. Upstream again. Bending magnet. Is it steering the electron beam off-center onto the target, creating an asymmetric photon beam before the filter? Possible. Even further. Electron gun. Microwave stability. Less likely to cause simple left-right asymmetry, but you keep going back. Knowing that chain done, accelerator, bending magnet, target, filter chamber gives you the places to look.
Perfect. It's a diagnostic roadmap.
That's a good way to put it.
All right, time for some rapid-fire clinical pearls.
Yeah.
The absolute must-know takeaways.
Okay, Pearl 1. Cobalt-60's big issue. Geometric penumbra. Driven by source size E's, depth D, and SDD. Remember, bigger source, deeper target, smaller SDD, all make penumbra worse.
Pearl 2. Know that LINAC sequence cold. Electrons generate microwaves in accelerators, bending to target foils, measured by monitors, shaped by jaws and MLCs. Burn it in. Gun microwave accelerator, bend target foil, line chamber jaws, MLCs.
Pearl 3. Flattening filter makes photons flat at 10 centimeters depth. Side effects. Beam hardening, hardest in center, and horns. High dose at edges, worse near Dmax.
Pearl 4. 270-degree bending magnet beats the 90-degree. Why? Energy selection, cleaner beam, and focusing, sharper spot, less penumbra.
Pearl 5. MLC leakage types. Mid-leaf, through leaf low, interleaf between leaves reduced by tongue and groove, and intraleaf between opposing tips can be high if they don't meet well.
And Pearl 6. IGRT doses. Know these numbers. KV planar ports, tiny, less than 0.1 centigrade. KV cone beam CT, like diagnostic CT, 1 to 5 centigrade. MV cone beam CT, highest dose, around 20 centigrade, and worse image quality.
Nail those 6, and you've got a solid grasp on some really key machine physics concepts.
Ready for a quick board review blitz? Test that recall.
Let's do it.
Question 1. Geometric penumbra from a cobalt-60 source increases if A. Source size decreases, B. Source surface distance increases, C. Source to diaphragm distance, or SDD, decreases, D. Depth decreases.
Okay, thinking about the formula. P sub G equals S, SSD plus DSDD, SDD. If SDD, the denominator, gets smaller, the whole value gets larger. So penumbra increases if SDD decreases. That's C.
Correct. Question 2. In a linear accelerator operating in photon mode, which component is primarily responsible for reducing the high intensity of the X-ray beam along the central axis to create a flatter profile?
That's the job description of the flattening filter.
Exactly. Question 3. Horns, areas of high dose near the field edge in a flattened photon beam, are most prominent at A. Deep depths, B. The flattening depth of 10 centimeters, CD max, the depth of maximum dose, D. The patient surface.
Horns are most prominent shallow, where differential hardening and lack of scatter are key, so CD max.
Perfect. Last one, question 4. What approximate dose might a patient receive from a single kilovoltage cone beam CT scan used for image-guided radiotherapy? A. Less than 0.1 centigrade, B. 1 to 5 centigrade, C. Approximately 20 centigrade, D. Greater than 50 centigrade.
KVC BCT. That's the one comparable to diagnostic CT. So B, 1 to 5 centigrade.
Excellent. You nailed the blitz. So we've gone from cobalt's history deep into the LINAC's guts, looked at how we shape and verify the beam, and why it all matters.
Yeah, it's complex, but understanding this machine physics is just so fundamental for practicing safely and effectively. It touches everything from planning to delivery to QA.
Absolutely. So let's end with a thought for you, the listener, to ponder. Given all this complexity we've discussed, especially around the flattening filter, how might the move towards flattening filter-free beams, FFF beams, potentially simplify the machine itself? But what new physics challenges might getting rid of that filter introduce, particularly for things like treatment planning and quality assurance?
Definitely something to think about as the technology keeps pushing forward.
Complete practice oral boards at RadOncsmartlearn.com and subscribe to RadOn Smart Review for our next episode. Thanks for tuning in.